Okay, so I'm gonna do just four problems. I'll do 1, 3, 11, and 14. So for number one, find two positive numbers such that their product is 192 and the sum of the first plus 3 times the second is a minimum. Okay, so there are two numbers I don't know. So let's get variables. What variables do we want to use? So X and Y, perfect. Okay. So what I'm going to do is let me get to a book because I don't have enough space to. Actually, I could do it over here. Here we go. This works. Okay. So X times Y is number one equals 192. And what else? X plus 3Y equals. Oh, it has to be minimum. Okay, got it. So let's call it actually we'll call it S for sum. Capital S will be the first plus 3 times the second. Okay. And this is what you want to optimize. More specifically, want to minimize. Sometimes you might have to maximize things. You might be asked to do that. Okay. So what do you guys think? What should I do? Yeah. So what we could do. See, you could actually graph this in Desmos, by the way, if you wanted to. But let's substitute. Let's say y equals 192 over x, and substitute. So x plus 3 parentheses 192 over x. Now, we could cheat a little bit and go to Desmos. And you could just plot that graph and find the low point. So if I call it like S of x equals x plus 3 parentheses 192 over x. And obviously my minimum is right there. So it's pretty clear. I can just get get the answer right away from Desmos, right? Pretty straightforward. But what we're going to do is we're going to use calculus to help us prove this.
But
Now,
that's wrong.
it's wrong.
No, the sum is 48 and the exponent is 48.
Right. I'm saying one of those numbers. That's all I'm saying.
Oh, yeah.
Right. One of those numbers. Anyhow. So yeah. So we have this, right? So now if you think about graphically, if I drew a line that's tangent to this point on this curve, what's the slope of that line?
Yeah.
It's horizontal. It's 0. Good. And the slope of a tangent line is what in calculus? The derivative. So if I took the derivative and said equal to 0, I could figure out the minimum, right? So we can use calculus to actually do the optimization. So that's what you want to do. You want to do some calculus here. So I'll call this S prime of X. Actually, before I even do that, let's prime this. It'll be X plus, what's 3 times 192? That's 576, I think. X negative 1. So if I take that derivative, what do I get? 1 minus 576 x raised to negative 2. And you're going to set it equal to 0. And what we're doing is we find something called the critical points. So the critical points, what does that mean? It's the x values that make the derivative 0. Okay, and then solve it. How would I solve it? Yeah. Yeah, so 576 over x squared equals 1. 576 equals x squared. If you square root, that should, I think it's perfect square. So 24. Yeah, it's 24. Okay, cool. So that means that x is 24. And remember, the product is 192. So then what's y going to be? 8. And that will minimize that value, that function of s equaling x plus 3y. That will be the minimum. So that's the beauty about calculus, is you can use calculus to prove these things without, if you didn't have a fancy calculator Desmos, the calculus actually helps you to prove why this makes sense. So that will be a way you can optimize it. So it's not too bad. I mean, it's really just a little algebra, right? You have to come up with the equations, you got to substitute. Obviously, you want to try to get all the, you don't want to get an equation in terms of one variable, then take a derivative, set equal to 0. And actually, I do have a process that I could print for you guys, because I actually have a list of steps you should follow. But here's the one thing, though, that I haven't quite fully been transparent about this. There's not a guarantee it's the lowest possible point. So all this tells us is just a relative min. That's all it tells us, right? So one thing you want to be mindful about, too, is our domain. If we think about originally what we had going on here, right? X times y equal 192. Now, if you think about the domain for x, right? And let's say they had to be positive. I mean, they didn't say that, did they? They did. Oh, you're right. They did, of course. Okay, great. But x can't be 0, right? So what if x was 0, then what happens? Yeah, the whole thing collapses, right? X can't be 0. Can it be awfully close to 0? Sure. But here's the problem. It's an open interval, not a closed interval. Because a closed interval, you're contained, and you can see, make sure the endpoints are not going to cause a min or max. When that happens, usually what you like to do is to take the second derivative and look at the concavity. So what was s prime of x again in this problem? What do we get? 1 minus 576 x to the -2 power.
Yes.
Okay.
I'm sorry.
Was it plus? It was minus, yeah. Okay, what's my second derivative going to be? Will be plus, where 576 times 2 is. What's that going to be? Uh, 1152 times x what power? Okay, cool. Now, in this domain, our situation here, what can you conclude about the concavity here? X is always positive, right? You put in a positive value here. Is the second derivative always positive, always negative, or is it change? Concave up, yep. There's always concave up. Just plug in a positive number. It stays positive. Yep. So what this tells me is that when I solved for x, I got 24. When we did a sign chart, we talked about this. The derivative was negative beforehand and positive afterwards, because if you plug in any number less than 24, does that make sense? What critical point is 24, right? Yeah. And yes, hold on. Do 1 minus 576 divided by. But yeah, no, that makes sense. Yeah, that will. Yeah, so that's what's happening with my derivative. Actually, let's put s prime, not prime. My apologies. So this is a relative min. Then we're concave up. if you're concave up the whole time and have relative min, it's probably more than just a relative min. We actually call it absolute min. Because it's that absolute lowest point. Yeah. So I do need to require you to do this verification process. But we're going to do this again on another problem so you guys get the hang of it. Some people find this annoying and they just want to get the answer, which technically, yes, that will get you the answer, just doing the derivative and just calling it a day. But you kind of have to do this verification. So meaning that, hey, let's explore the domain. What's going on here? And the cool thing is that we're going to do a couple of geometry problems where it's a physical situation. You'll see that physically, yeah, this has to be the domain. But how do we prove it's not just a relative min, but it's the truest lowest point? You got to do a second derivative. So, but that's how you can verify it. So it's a great way of reinforcing a lot of these things we've done. So this actually is, in some ways, I'm actually preparing for the final because we have to do these kind of things, right? Second derivatives and first derivatives and whatnot. So, yes, so now we got it. So now we know for sure, right, with certainty, 24 and 8, right? If it satisfies the condition, and it will minimize the sum of the first and 3 times second number. All right, can we move on to the next one? Right, okay. I'm gonna do number 3 with you guys. Yeah, you can see right here, yeah, 24 and 8. Okay, let's do number 3. Let's get into a little geometry now. Okay, so this is very practical. Actually, we used to use Dr. Slafter and Doyle's in our AP calculus test. So these are some of the word problems. So you can, if you ever go to like the garden, like on the other side of campus where the preschool is, at the corner of Emily and Valparaiso, and then usually there's the Donohoe Grove, and they'll have like the goats that are grazing and have an enclosure. So, yeah, that would be, I think, something that Dr. Slaffer or Mr. Fitchburg would be interested in knowing. Like, hey, what kind of, if I have to buy a certain amount of fencing, or if I have a certain amount of fencing available, like you find like someone donate a bunch of like posts that said like build a fence, how can I design this enclosure to maximize the area? Do you want to maximize the grazing area for the goats and make you don't get hit by the cars, right? So anyhow, Darren wants to make return enclosure using a wall as one side, 100 fencing for the other 3 sides. Express the area in terms of x, and find out how that gives greatest area. Okay, good. All right. So let's say I call this x, x, and y. And let's say this is the wall. Could the wall have been the other side, like maybe the vertical side? Sure. Remember, this is all hypothetical. It could all change. It will all work itself out. So don't worry if you put the wall over here or here. It won't matter. In the grand scheme of things, will not matter. Okay, so that's what's happening. So now let's think about our formulas, right? What formulas can I make based on this information? Okay, that's area, right? And what's our goal here? To minimize or maximize it? Good. What else do I know? So 2x plus y equals 120. Awesome. Very good. Okay, so what do you think I'm going to do? Let's substitute. Yeah. So if I substitute, let's get the area in terms of y. Sorry, area in terms of x. My apologies. So if I substitute, what's y going to equal? 120 over, that was dumb. 120 minus 2x. My apologies. 120 minus 2x. So area is going to be x times 120 minus 2x. Now, I don't really need calculus to do this. If you think about it. What kind of function is that? Quadratic probably highs and lows. Yeah. And what are my x-intercepts? 60. So what's my vertex? 30. Good. And this is a problem opening up or down. Down. So the vertex is vertex of max or min. And the highest possible point. So where's my max happen at? So I'm done. Technically, I'm done. But I won't go into season. It's a little too easy. But it's just to show you why this how calculus can play a role. So I know what's going to happen.
Yeah.
You did some Mr. Band's class?
We did one where it was like
Okay.
Build a fence on 3 sides.
Good. But here's the deal. You can also use calculus too. because you want something that's ubiquitous that you can use for any kind of situation, like any kind of modeling a formula, right? So x equals 30. So I just did it. Found the derivative, z equals 0, solve for x, easy peasy, right? X equals 30. Cool. So this means that y is going to be 60. So my dimensions have to be 30 feet by 60 feet. So we'll satisfy the perimeter. Sure, remember we have a wall, mind you, we have a wall. That makes sense. Yeah. And the area would be 1,800 square feet. That would maximize. So that's how you have to build your fence. Now, can you build the fence differently? Sure, you can make it super thin. That'd be dumb. Like make X really small, Y really wide, or vice versa. Like that wouldn't make any sense whatsoever. You could. Now, how do I prove this? That this is truly the best option? You take your second derivative, which is what? And of course, you're always concave down. So for all, and my domain, by the way. Now, there is actually a restricted domain, by the way. If you think about this formula here, 2x plus y equals 120, what if x were 60? You could do that. Why not? You'd have no y. You could, but if x were 60, 0, what's your area? Yeah, you could. It'd be super dumb, like make it like this. You could. And of course, x could be 0 itself, and y could be 120. So the domain is closed. So there's a theorem I haven't taught you guys. I don't want to teach you guys this year because you guys will see it next year. It's called extreme value theorem, or short for EVT. Extreme value theorem states that extreme values happen at endpoints or critical points, assuming you have a continuous function on a closed interval. Is this going to be continuous? Sure. Yeah, of course. In the domain, right? In the domain, it's fully going to be continuous. 100% will be. So yeah. So you got your critical points, you got your endpoints. So you could test 0 and 120, but it's a waste of time. The no error is going to be 0, so I'm not going to bother doing that. But at least it proves to me, okay, yeah, this is definitely because that's a restricted domain. Those endpoints are not going to minimum area, not maximum area. So I have that. So that's yet another way. And I'll give you guys some like model solutions to look at that involve optimization. I'll pull it up when I get a moment. Actually, we'll see it now. I'll show you my I should have printed. I'll have it ready for you guys by Wednesday. Let's see here. It's gonna be, what was that? Created. I'm just talking fast. Mumbling. Let's see here. It's gonna be, yeah, COVID year. That's when I taught this class. Crazy time. You guys were like you guys were in 5th grade COVID? 4th grade? Oh, I feel bad for you guys. That's terrible. All right. That's gonna be, hold on. No, it's not this one. Hold on. Here we go. Yeah, here we go, guys. So these are like the filled out notes. It says try drawing a picture, list information, decide what you got to maximize, minimize, come up with a formula, figure out your domain, analytical solutions, you do the derivative, state it afterwards. But yeah, I'll share this with you guys so you guys have access, and I can kind of give you some worked out situations and how to approach it. So
Is this like what an APFRQ is like?
actually, they don't do this in FRQs optimization. It's actually very seldom tested on the AP. Maybe it's multiple choice. You might see something like that, but It actually for a long time it was not an AP exam, but we still taught it anyway. It's my favorite of all the calculus topics to teach, um, but I think they brought it back. I highly doubt it will be an FRQ. Maybe if like one part of it, but okay, let's move on to two more problems. You guys can do some practice problems. So now I'm gonna give you guys ones that are a little more challenging with 3 dimensions. So let's look at 11 and 14. Okay, 11. So let's go with 11. A manufacturer wants to design open box. Okay, so box has no lid. Square base. Okay, fine. Surface area of 108 square inches. So it's going back to geo. I don't know. We got to figure it out. So we'll figure it out. What dimensions will produce a box with maximum volume? So you want to maximize it. So if you think about it, well, we got a piece of cardboard and you cut out some corners and try to fold it, right? How are you going to fold that box? Maximize area because you maybe need this box to put stuff in, right? So you want to maximize, you don't want to waste material, right? So this is kind of a good example. So let's go down here because I need some more space. Okay. So, oh, you guys did something like this? Cool. Yeah, I like that. But you didn't do calculus with it though. All right. Here's your box, right? I'm not a good drawer, but I think I do 3D okay. So you kind of just draw two rectangles kind of like that, off-centered. Okay, so I'll call this X, X, and Y. I could do that because you see they have a square base, right? I could do that. Now, you asked about surface area, Avery. Don't worry about formulas, just use logic. What's the area of the base here? X squared. And you have 4 of the faces where shapes what? That's rectangle, that's what. There you go. Yeah. So the area, and there's no top, by the way. So you don't do X squared twice. X squared plus 4xy. Then also the volume. Actually, I know it's 108. I'm tripping. Sorry, that was dumb. I know it's 108. Let's put 108 right away. 108 equals x squared plus 4xy. Volume is x squared times y, right? We're okay with that? And we want to maximize this. Okay. So how do you think, what do you think I should do? For what? Yeah, either get y by itself, I'd agree. So 4xy equals 108 minus x squared. What does y equal? Okay, so y equals that. So my volume in terms of x clean it up. You should get x times 108 minus x squared over 4 because x's cancel, right? And you could probably go a little further with this. That's what 27x minus 1/4 x cubed. Would you guys agree? Okay. Now, what you guys in Mr. Band's class, you guys would graph this. And the graph would look something kind of like this. And then you find the peak and you're good, right? We're not going to do that. Even though we know graphical is supposed to happen, we're going to use calculus, right? But so far, we're okay. Is everything? Okay, cool. All right, so let's take our derivative. What's our derivative? 27 minus what? Okay, set equal to 0. Move things around. You should get x equals 6. If you do it correctly, you should get x equals 6. But just to be sure, Let's do a sign chart for V prime. If I plug anything less than 6, it's gonna be positive, then negative. So this guarantees it's a relative max. If I look at any critical points here, X can't be 0, right? That'd be a problem. If X are 0. Because then how are you gonna get 108? That's impossible. It could be close to 0. And X could be yeah, actually, because Y can't be negative. You don't want to get you don't want X to be too high. If X is too high, then Y is negative, right? So it can't be more than root 108. Because physically Y is negative, then that makes no sense, right? So I know my domain. But it could be awfully close to 0. That's a possibility. It could be super close to 0. And root 108. And it could be root 108 exactly. I mean, it'd be weird and Y be 0, but you could do that. That's possible. But because it's not a closed interval, we can't really quite make that conclusion that's going to be the absolute maximum. So what do? We do our second derivative. If I do my second derivative, let me get rid of the diagram here. What's the second derivative going to be, guys? It's a negative 3/2 x, right? And for my domain, we're always concave down. So if you're concave down, guess what? Now I know in my domain, I'm always concave down. That's going to be the absolute max. That's how you verify it. So the dimension of the box, if it's X is 6, it's a 6 by 6 by 3. Remember, it has to involve almost by 108 strips area. So that's 36 here. This will have to be 72 equals 12y. Wait, does that make sense? Hold on, 36. That's 24. Sorry, my apologies. 72 equals 24y, y can be 3. So you need to create a box that's 6 by 6 and 3 high. So our volume function, which was over here, that got terms of x, our line function is always concave down in this interval. Because it's concave down, that means that when you found the horizontal tangent, you know that's going to be the highest possible.
How does the second derivative prove that it's concave down?
Oh, because they have x. And
Absolutely.
you put an x has to be bigger than 0. Right? It's physically, right? X can't be negative. You're doing geometry, right? And then how do I know root 108? Well, I got y by itself. X is more than root 108. The top is negative. So you kind of just find so it makes that 0. Okay, last one. And you guys can do some work. Hmm? No, it always does. It always does. Just have to. Yeah. Okay, last ones. Let's talk about 14. Okay, 14. All right. This is a cool one too. A cylindrical metal container open at top is at a capacity of 24 piping. So let's say you work for a cannery, and that's what you have to do. Like you have to save some money, right? A cannery. Like Monterey, there's a famous like cannery down there. A canary, yeah, okay. The cost of material used for the bottom of the container, like maybe using some sort of fancy metal for it, is 15 cents per square inch. The cost of the material used for the curved part, the lateral area, is 5 cents per square inch. Find inventions that will maximize, sorry, not max, but they'll minimize the cost of the material and find that minimum cost. Does that make sense? In business, you want to save money, right? So that's what we have to do. So let's talk about this one here. And most likely for the project, I did this like a long time ago when I taught non-AP calculus. Um, we could probably do like a pizza theme, and maybe I could bake you guys pizza too. I could do that. That'd be fun. Okay. um, so if you think about pizza, what are some things you have to have? You have to have pizza boxes, right? And how do have you guys seen how they make pizza boxes? It's a flat cardboard and they fold it. But before it's folded, when it comes from the manufacturer, there's certain holes cut out, right? And they have to cut out like, or they have to cut out certain corners, sorry, so that it folds, so it folds correctly. But you want to cut in such a way to maximize the volume, right? Otherwise, you're wasting material. Or using tomato sauce, right? We love what's pizza without tomato sauce, right? But the manufacturer makes a can, they gotta save their money, right? So anyhow, this will be kind of a fun thing to do. So correct, 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 correct. It is. All right. Okay, so here you got a can, right? Now, what are the dimensions we care about, guys? R and H. Okay. Now, capacity. That's volume. Volume is going to equal power squared H. And by the way, don't worry if you don't remember these formulas. I'll give them to you. Don't worry. Volume equals power squared H because it's area of the base times the height. Now, the cost function, I'll call it capital C. It's kind of like surface area in a way. So for the bottom, it's 15 cents, right? Per square inch. What's area at the bottom? So you're going to do 0.15 times power squared. Plus, now lateral area, don't worry about if you don't know. Do you remember the lateral area? The point for that? Wow, look at you guys. Awesome. By the way, the best way to figure that out is it's the perimeter of the base times the height. But because the base is a circle, the perimeter is like circumference. So you 2 pi r times. Yeah. Cool. All right. So I want to minimize this. By the way, I've been incredibly consistent every time. Diagram, want to optimize, and then take my constraints. Right. Oh, by the way, the volume, we know it's 24 pi. By the way, what happens to the pi's? Probably best to substitute for what then? So 24 over r squared. So C, in terms of r, will be 0.15 pi r squared plus, and then what's 0.05 times 2? It's 0.1, right? 0.1 pi r times 24 over r squared. Should probably clean this up a tad. Let's clean it up. Plus 2.4 pi over r. Okay, take the derivative. That's me 0.3 pi r. Sorry, I should have cleaned this up a bit more. That's 2.4 pi times r to what power? -1. So it becomes minus 2.4 pi r to -2. Set this equal to 0. While we're at it, let's actually factor out 0.3. Make our lives a little easier. And, so factor out 0.3 in pi. So what does that mean? R minus 8 over r squared has to equal what?
Yeah.
And I trust you guys can do this. You cross multiply, work it out. You should get 2. Comes up really nice and clean. Like r equals 2. What's your height?
6.
Yep. Cool. And then you get the cost. When we get the cost, I could probably do it over here. Just trust me, I'm cheating. I have the answer in front of me. If you plug in 2 for R, work it out, you get that. So that'll be the minimum cost. I mean, that's kind of crazy. I think this must be like a really big hand or something. Yeah, that just seems kind of ridiculous. That shouldn't cost that much money, but anyhow, maybe these cost values are a little off. But anyhow, that's what's happening. So now how do you prove it? You could look at the domain, but again, R can't be 0. So, and R could be really a crazy big number. So domain for R is open. If it's closed, you can just test the endpoint and then guarantee that, okay, those are not going to be the max or min, whatever. So the best thing to do at this case is then to do a second derivative. If I do a second derivative, I get 0.3 pi plus 4.8 pi r to -3. If you were to plug in any value that's bigger than 0 for r, it's going to be positive.
Wouldn't R be limited to
No, because r could be super, h could be super tiny. You can make h really, really tiny. You have cans like this. It'd be weird. Radius like that. You could do that. It'd be hard to manufacture, but you could do it. So you're always concave up, given the what the second derivative became. So if you're always concave up, then this relative min is actually not true. Okay, so I think it'd be kind of cool to have you guys do the rest of these for homework. So I'm just gonna kind of be somewhat selective here. Let's say we'll have you guys do 2, 4, 8, 12, 13, and 15. And we'll talk about those in class on Wednesday. But this is just so you can practice doing this, and then we'll talk about the project on Wednesday. I won't put this on the final. This won't be a final exam question, unless you guys really want me to. But no. But anyway, I just this is kind of a neat application of calculus. It's one of my favorite applications of calculus. So, and now you can actually see how math can be used in the real world. Maybe, kind of, I don't know. So,
Mr. The final poll with your final is about.
do you guys want to put polar stuff on there and vectors? And why not? Parametric, no. Trig identity, it's not that. Come on. Don't triple quadruple angle. All right. I don't know that. No, it's not. No, this is gonna be a calculus. It's gonna be like a calculus test with some sequences in the series. So it'll be calculus heavy. So
Right out of students problem for like one year, or like you're really not considering
what?
like any of the optimization.
No, this is a project. Yeah, it's just a project. So anyhow, yeah, so if you guys want to work on those problems now, we can still got another 12-ish minutes. But yeah, there you go. Optimization.